have here 2 or 3 microsomes, so every time I am checking if it works. Something to write. One. Okay, so we'll start discrete mathematics lecture second. Discrete mathematics. So today we'll continue working on the basics of calculations in discrete sets. Namely, I would like to show the method of proving by mathematical induction, so inductive proofs. And next, we'll have integer functions as ceiling and floor, which are very useful for changing calculations from real numbers to integer ones. And here, application of floor as ceiling, and next asymptotics. Because in the next part of the lectures, we'll show some algorithms, and talking about algorithms is necessarily connected with computational complexity discussion. So if we would like to talk formally about computational complexity, we should invite some method of writing or denoting it. And this will be connected with the notation of big O, theta, omega, small omega. Yes, so mainly theta and big O. Okay, so this is the plan for today's lecture. Firstly, let's start from the inductive proof. As usually, just a second, I have something on the chat. Morning. Okay. So if you have a possibility to turn on your web cameras, this is very pleasant for me to see if my teaching works. So if not, it doesn't matter, but usually it is better for me to talk to the people and not to the plastic lens or something. Inductive proofs. Okay, so this is in fact a kind of axiom of the mathematics that we assume that we can always add one and make some kind of formal steps to show that if it works for some set, it will also works for the bigger one. So induction, it is formally a method of proving, but some kind it is a basics of discrete mathematics and mathematics at all. Induction, mathematical induction. Maybe I will write firstly how it works. So such an inductive proof so this is such a method of proving in which we have some property we would like to prove, and this is the logical sentence showing that the next property for the next natural number starting from someone also works. Maybe I will write it in formal way. If there is a natural number n, let it be n0, such that step 0, we have some property. P from n0 is true. P a property we would like to prove. Step 1. This is so-called inductive assumption. We assume that this is true up to this n0 number. Step 1. Inductive assumption. For any natural number k greater or equal to n0, pk imply pk plus 1 is true. Step 1 and 2. So this is so-called thesis. P from n is true. For all n greater or equal n0. So formally it looks like this, that it exists and n0 belongs to natural numbers, that we have such a thing. P from n0 is true, and for all n greater or equal n0, P from n is true. That means that P from n plus 1 is true. So from this whole sentence, we have that for all n greater or equal n0, P from n is true. The end of the parenthesis. So here we have written, the same as this. This is the formal way. This is for all. Oh, maybe I'll write it right. Okay. This is for all. This is, it exists. Yeah. Because this is the letter A for all, this is E, like in exists. If it is understandable, this is clear how it works. Maybe we should better see it on an example, because formally this is just a formal construction. Yeah? But better, let us show on an example. The induction is very useful for showing some properties of natural numbers, because it works mainly for natural numbers, not for real one. So it is very useful for natural and integer calculations. Example 1. So let us try to show that proof that the sum from 1 plus 2 plus 3 and so on plus n is n times n plus 1 divided by 2. Of course, this is very well-known equation. The history connects it with small Gauss, really small, because the history is that the Gauss has about 7 years old, and he was in primary school, and the teacher said all the pupils to calculate the sum of numbers from 1 to 100, because he would like to have a free time on the classes. But after 2 or 3 minutes, Gauss, 7 years old, so the small one, showed the result. As I remember, it was 5,050 or something. Yes. So it was very strange for the teacher, because he assumed that it takes an hour to calculate the sum of numbers 1 plus 2 plus 3 plus 4 and writing it. But the observation from the Gauss was that if we have such a sum, plus 98 plus 99 plus 100, so if we have 1 plus 100, this is 101. 2 plus 99, this is also 109. 3 plus 98 is 101, and so on. And we have how many? 50 such a sum. So the result is 50 times 101, so this is 5,050. But of course, this is not inductive proof. This is just a trick. But this is very, very, very easy to see that this is n by 2 times such a sum of the first and the last element. You can easily see that this always will be natural number, because if this is even, this is odd, and if this is odd, this is even. So every time this will be natural number, but this is just a trick. We'll show this equation formally from mathematical induction, but it is easy to see that it works. Yes, that this is n by 2 times the sum of the first and the last element, so it works. But formally, it will be like this. This is a trick. No, this is here is no induction. Induction will be now. So let us, inductive proof looks like this. Proof by induction. So we have 2 steps. The first step is assuming that this is true, and check. Step 0, checking if it works for the first one. So for n equals to 1, we have here is sum from 1 to 1. This is 1, and from the right side we have 1 times 2 divided by 2. So this is 1. Okay, it works for the first one. Now we should assume that the equation is true and check if this is also true for the next n. So inductive assumption. Let's assume that this equation is true. For n0 equals to 1. This is n0. Okay. We will show that it works for let it be k for k plus 1. Okay, so we have like this: 1 plus 2 plus 3 up to okay, let it be k plus 1. And now, from the assumption, we have that this one is k plus times k plus 1 divided by 2 because it was the assumption. So we have k times k plus 1 divided by 2 and plus k plus 1. Let us make the common denominator. In the fraction, we have here, this is numerator and this is denominator. Numerator, denominator. This is fraction. Okay, so let us try. So we have this is from assumption. So let us take k plus 1 divided by 2 plus 2 times k plus 1 divided by 2. So this is k plus 1. Here will be k plus 2 divided by 2. Okay, this is the equation for the n equals to k plus 1. N plus 1, n plus 2 divided by 2. Okay, so it ends the inductive proof because we have assumed that it works for all the n up to some number. Oh, here this is 1. But for some equation, it works from some place, not necessarily from 1. Sometimes it can work from 7. For example, if we have an equation like, let us see something. The n to the power of n plus 1 is greater than n plus 1 is to the power of n. I suppose that such an equation works from some place, not necessarily from 1, because from 1 here is 1 to the power of 2, and here we have 2 to the power of 1. So this is not true. But for 2, we have 2 to the power of 3, so this is 8, and here is 3 to the power of 2, this is 9, also not works. For 3, 3 to the power of 4 is, I don't know, maybe 81. What is 3 to the power of 4? Hello?
It's 81.
Yeah. And 4 to the power of 3? 4 times 4, 4, 16.
64.
Yeah, so it works. So probably it works from n0 equals to 3, I assume. And it is easy to prove that it works, but not from 1. From 1, for 1, this is not true yet. Okay, so from the an axiom of mathematical induction, because this is not even the theorem, this is axiom. We have that if we assume that this is true for some set and show that for the next one also it works, we have that it works for all the natural numbers, as here we have from some place. For all n greater than n0, and here n0 is 1, so this is true for all the natural numbers. What was to prove? Okay, another example. Maybe this one, but I suppose that this one is not easy to prove. Maybe let us not take it as an example of the lecture. We can take it to the exercises, but this is true for n equals or greater than 3. But this is not easy to prepare, and making the proofs just by hand here. This is not a good idea. The lecture with this in real life online. So the exercise 2, exercise example, not exercise. Example the second, proof that 2n plus 1 is greater than 2 to the power of n for n equals or greater than 3. So, like in previous example, step 1, n equals to n0 equals to 3. We have 2 times 3 plus 1, so this is 7, and this is greater than smaller than, oh yeah, sorry, smaller than 2 to the power of 3, which is 8. Okay, it works. So let us assume that this is true. So this is our 2 asterisks. So this is our assumption. And now the second step. We assume that this is true and show the calculation for the next n or k. Usually people change the letter in mathematics, in inductive proofs from n to k. I don't know really why. Maybe formally this is okay, because in another case we should write that n equals to n plus 1, which mathematically has no sense, yes, except n equals to infinity and minus infinity. So let us use this case, this case. Let us assume that 2 times k plus 1 smaller than 2 to the power of k is true for k equals to 3. Okay, or even smaller than. Sometimes this is important that we assume that it works not for n0, but also for smaller than n0, or from some place, Okay, so this will be for k. Oh, let it be equals to n0 equals to 3. Okay. Next, let us check for k plus 1. For n equals to k plus 1, we have n times k plus 1, which is 2 times k plus 2. This one, from assumption, is smaller than 2 to the power of k. So we have that this is smaller than 2 to the power of k from assumption, so from this one, yeah, plus 2. So this is 2 to the power of k plus 1. So we have this part, and this ends the proof. Is it understandable? I suppose this is quite easy, and we frequently use mathematical induction to show some a little bit more difficult equations. Maybe I will write some of them here. You can try this one if you want, or we have also a nice equation for 1 to square plus 2 square plus 3 and so on plus n square. It should be exactly, but just a second, I will check it. What is the sum of squares? As a exercise, just because it is easy to prove true equations. If it is not true, better also. Yeah, n plus 1 times 2n plus 1 divided by 6. Yeah. So there is also such a true equation, and the way of proving it is induction. I think this is as in this trick on the beginning from small Gauss. Yes, in a situation like this, this is not easy. This can be proved in some way combinatorially, probably, but by induction we just assume that this is true. Show for n equals to n plus 1, so for up to n plus 1 square, and somehow we obtain the equation on the right side which works for n plus 1. This is the easiest way. Okay, so this is induction. Just a method of proving some states, some such statements for integer or natural functions, which means function which have arguments being natural numbers. We should remember that it doesn't work for real numbers. If we have just real number function, it is not the proper method of proving, because induction is in fact another definition of natural numbers. In other words, and the infinitiveness of the set of natural numbers goes from such an assumption that we can always add one. Okay, any questions to induction? So let's go to floor and ceiling functions. A very useful tool for changing real numbers to integer ones and calculate on them. Frequently we can use such a function, for example in Excel, in Microsoft Excel, to change the result of some calculation up to natural one. The simplest example, if we calculate mainly, I have to write final marks students from some courses on the end, and I have to calculate the grade, the mark being the average of the laboratory and lecture. And usually I use to it the floor or ceiling function, calculate the approximation, because if we have, for example, 4.5 from the laboratory and 5 from the lecture, we have as an average 4.75, and we should make from it 4.5 or 5, not as a final mark, because we have only this discrete set. So to use it, it is easy to calculate this as let us assume that this is A and this is B. Yes. So we just make something like this, that we calculate A plus B divided by 2. And next we have to make an approximation, for example, like this, that we make it a ceiling from it. So this is the nearest maybe before. Okay, maybe let us make like this. If you make like this, we have 4.5 plus 5 divided by 2, so this is 4.75. If we make an approximation, so we have 5, and this is it. Maybe like this. Maybe we have some other way. Maybe 4. I don't remember really now how to do. Maybe this is okay for the students, but I don't remember exactly, because as I remember in Excel, sometimes I make such a trick to make an approximation to the nearest integer, multiply by 2, and next divide by 2. Also, we have dividing in natural numbers. So maybe, as I remember, such a function div, it works like this, that we have, for example, 5 divided by 2, so this is 2, yeah? Because this is without the rest. Okay, somehow such a function of approximation to the nearest integer, lower on greater, is useful. Sometimes if we would like to make a discrete set like this, not 4.75, but having just 4 or 5 or 4.5 if you want. But generally, mainly we have 3 such a functions: floor, ceiling, and entier. And all of them are predestinated to being used in different situations, but if we know how it works, we can use them changing eventually in between. Okay, so as an introduction, maybe like this: integer numbers are the basis of discrete mathematics. We are often forced to convert rational of real numbers or near rational or real numbers to integers. Such transformations are integer functions. Integer means that the result is an integer. Floor and ceiling. Floor means floor, ceiling is ceiling. So floor makes the nearest lower number, lower or equal, because the floor from, or maybe just examples. Floor from 3.14 is 3. Ceiling from 3.14 is 4. And here, this is a little bit different function, but let us begin from this easier ones. So formally, we can write how it works.
Excuse me?
Yeah.
And the ceiling of 3 would be 3 or 4?
The ceiling of 3 is 3.
That's the floor.
And the floor of 3 is also 3. So for integer functions, it doesn't change anything. Only for not integer, it takes the nearest greater or smaller.
Okay, thank you.
Thank you for this question, because I have forgotten to say what happens if we just take the integer. Another strange example is negative numbers. If we take minus 3.14, the floor will be minus 4, because this is the nearest integer smaller or equal. So smaller than minus 3 is minus 4. Yeah? And ceiling from minus 3.14 is minus 3. So it takes the nearest, like here. Yes, we have 0. Here is minus 3.14. And the nearest integer here we have minus 4, lower. This is minus 3. And for the positive ones, also we have 3 and 4, and taking this one which is smaller or equal. I will write the definition and it will be clear, because it is somehow intuitional, but for negatives number, we should remember that this is not symmetrical. Yes, like this, because this is from negative 1, this is not minus 3, but minus 4. So floor function floor. The symbol is like this. Maybe let us like this. This is lower integer rounding. So let us take the real number x, and the floor from x is maximal k belonging to integers, such a k is smaller or equal to x. So if we have a number like here, we take integer number which is lower or equal, and it is maximal. So -7, -6, 0, 1, 2, 3 is maximal from them, because the next one, 4, doesn't fulfill this inequality. So this is maximal one we can take here. And also we can see that if we take an integer number, this will be the same number. Yes? Because if x is integer, this is just the same because it equals here. That's why floor from 3 is 3. So this is just a definition. We have some properties. We can see that x, if this is k, we can see that k is smaller or equal to x, and this is smaller than x plus 1, k plus 1. So this is between two integers. The first and the second will be like this. If this is the floor is x, this is the same that k is between x minus 1 and x. Here we have smaller or equal. Here we have strong inequality. This is just property. Sometimes we also define difference between the fractional part, and we call it fractional part of the x. Maybe I will write it. X minus floor from x. This is maybe like this. Fractional part of x. However, oh no, it is okay. However, for negative ones, this is a little bit strange, because for positive ones, for example, here the fractional part will be 0.14 as the difference between 3.14 and 3. But for negative ones, this fractional part will be what? 0.86 probably. Yes, because this is -4. What? This will be even, yeah. This will be no, with a negative one. Oh yeah, like this. It looks strange. Yes, negative ones. Yeah. So fractional part, it is intuitional for positive ones. For negative, we assume that this is fractional part. Yes, this 0.14. So such a definition is not very intuitional. Okay, what time? 5 minutes yet to the break. So the ceiling definition. Ceiling. So the ceiling will be symmetrical, the nearest integer which is greater or equal to the number. Ceiling function. So this is upper integer rounding. So we have x equals to real, and we have the ceiling is minimum k belonging to integers, such a k is greater or equals to x. So this is nearest integer number which is greater or equal to x. Also some properties, like here, if we have the ceiling of x and this will be k, so we have that k minus 1 and k rounds as an x, but here we have a strong inequality, and also we have such a property, x smaller or equal to k smaller than x plus 1. And then examples, for example, ceiling from minus e. This is a limit of 1 plus 1 by n to the power of n, and this is approximately 2.71 something. So if we take it from minus e, this will be minus 2, because this is the nearest greater integer. Ceiling from 5 is 5. Ceiling from 1.7 is 2. Is it clear how it works?
Yeah.
Yes.
Oh, okay. Okay, this is 2 to 10. So let us make a 17 minutes break, up to 15 past 10. So break for the tea or coffee or something. Something stronger. Oh, I'm back. Sorry. I'm back. This was the sentence of the Terminator, as I remember from the movie. Okay, so I'm back. We have ceiling and floor functions. Now, let us illustrate how it looks like, because the graph is quite interesting. Okay, so let's just take the floor function. If you would like to floor, to make a graph of it, it looks like this: 0, 1, 2. X. Oh, this will be floor from X. So, if we have the numbers from 1 to 2, we have from 0 to 1, we have here. In 1, we'll obtain 1. To 2, in 2, we have 2, and so on. So, such a stairs are the graph representation, the graphical representation of floor function. Similar here. Yeah, we usually write here in such a cases like such an empty circle here. Yeah, so this means that in the point 2, the value is not 2. The value is not 1, but the closer, infinitely close to 2 from the left side, we still have 1. Yeah? Something similar here. Yes, so this is the floor function. Similarly, if we have ceiling, it will looks like this, maybe green one. This. And so on. So such a cases mean that here we have the value in the point 1 is 1, but in 1 point something, 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 something. 1, this is 2. So this website is. Some properties of floor and ceiling functions. Properties might be here. This. Floor from minus x is minus ceiling from x. Ceiling from minus x is minus floor. Oh, of course, we can prove it, but this is just as a simple properties. Floor from n times x is not n times floor from x if n is integer. So this is important because this is not possible to take the constant before the floor or ceiling, similar from ceiling. And we have such a that floor from x, ceiling is similar. If this is true, that floor is from x is x, that means that x is integer number. Oh, this is quite easy. Similarly, ceiling equals to x. Okay. Just a second here. Yeah. If we add a number, this is true that ceiling from x plus n is ceiling from x plus n. So we can take the constant, but add it or subtracting from number, not multiplying or dividing. So this is true. N should be an integer number. Integer. Okay, is it clear? Is it visible?
Yep.
Yes.
Okay, thank you. Oh, an application of this function, quite connected with computer science. Let us assume that we are asking how many bits we should have to denote a number. How many bits? For example, if we have the numbers from 0 to 256, we have 8 bits. Yes, because this is logarithm with the base 2 from 256. But if we have any interval, the question is how many bits we should have, because the number of bits, 0 or 1, is a natural number. So the result of such a calculation should be natural. So as an example, example 3. How many bits does it take to write a natural number alpha in binary form? Let's reverse the question. In other words, what is the largest number that can be written in n bits? Of course, such a number in binary expression, this is just ones. Sorry, this is not a virus, I hope. So we have to take a number of n's of ones, and the value of such a number will be of the value bits of the value 2 to the power of n minus 1 plus 2 to the power of n minus 2, and so on, 2 to the power of 1, 2 to the power of 0. So this can be written as 2 to the power of n minus 1. It is easy to show that the sum of such a geometrical sequence is 2 to the power of n minus 1. It doesn't matter here how to prove it. This is quite simple. But let us try to write the number of bits if we have a number alpha. So hence 2 to the power of n minus 1 should be greater or equal than alpha. That is 2 to the power of n should be greater than alpha plus 1. So taking logarithm, we have n should be greater or equal than logarithm with the base 2 of alpha plus 1, but we should have a natural number of bits. The n is number of bits. So finally, we need ceiling from the logarithm with the base 2 from alpha plus 1 bits. So this is the nearest integer number which is greater or equal to this logarithm. If n is a power of 2, it doesn't matter, we just obtain a natural number here. But if we would like to write the number 257, we should have 9 bits, because from this logarithm we will obtain 8 point something, yes, and the ceiling will be 9. Okay. Is it clear? This is just a simple example. Okay, thank you. And now let's go to the asymptotics, because using natural number functions is usually connected with some properties achieving in the infinity. And if we calculate, for example, computational complexity or some property, how the system, doesn't matter which one, the system behavior for great numbers, it is very useful to knowing what is the asymptotic behavior of a function, where it goes for great numbers, if it goes to the infinity. So we call it asymptotic behavior, and it will be connected with the notion, the noting of the limit behavior of complexity. For example, for if we have the time which goes to the infinity. Okay, so let us observe such a function, asymptotics. Example 5. Let us observe a factor of a number. Where can be estimated so we have n factor as 1 times 2 times 3 and so on, times n minus 1 times n. It can be easily estimated, approximated by n to the power of n. Yes? And truly, this function grows very fastly, and its behavior is very similar to the behavior of the function n to the power of n. We can also more accurate estimates, n to the power of n by 2, smaller than n factor, smaller or equal n plus 1 by 2 to the power of n. Such inequalities in estimating can be complicated. In asymptotic approach, we generally accept some special symbols which can write us what is the main part of this this function in the infinity. For instance, if we have the function example 6, if we have a function 17 times n to the power of 100 plus half times 2 to the power of n and plus let it be n to the power of 3. Yeah, so we have many elements of many parts of this function, but if we go to the infinity, so in fact this n to the power of 3 doesn't matter. It does, but mainly this one. Yes. So we write it as the big O from 2 to the power of n. Why? Because for greater n, this part is only the important one. The rest will be the rest will be much smaller. Of course, n to the power of 100 looks very great, very fastly growing, but in fact, every polynomial function from some place will be smaller than exponential one. So in a notation of asymptotic behavior, which we would like to see what is the main part of the function. From the application point of view, if we have, for instance, sorting algorithm, let it be quicksort, so we should observe what is the number of comparison inside, or the number of adding products, multiplying, and so on. We can calculate them, achieving a function which is dependent on the number of elements to be sorted, and it will be very complicated. But in fact, for grower number of n, it is connected only with the one part. For instance, if we have quicksort, we'd observe that the number of comparisons will be as n squared. For merge sort, we'd like to write that there will be n log n, and so on. Of course, for quicksort, the average in complexity is also n log n, but only if we can find so-called pivot in the right way. Pivot is in quicksort this element with which we compare other elements, sorting, making the partition to the two parts. So it doesn't matter. Quicksort is just a sorting algorithm, but its pessimistic behavior is n squared. Okay, so we need a denoting for such situations. And the main function used here is so-called big O, this one. How it is defined? Asymptotic notation. Function asymptotically less than, just a second, maybe not greater than. G on from n is the function f from natural to real numbers, for which there exists c, a real number greater than 0, and n0, natural number, such that the absolute value for f of n is smaller than c times absolute value from g from n, and it holds for almost all natural numbers n. And it looks like this, that if you have a function f, which looks like this, and we have the function g, like this. So it is important that from some place, we call it n0, the function g is greater than the function f. In fact, here we have the constant because sometimes it is important, but the definition and this almost all means all from this place n and greater. So formally, we write this like this, that f from n is big O from GON, and this is the same as we write that it exists a constant C, and it exists a natural number n, that for all n greater than n0, we have that f is smaller than t times g by n. An example, the sixth one. If we have the function f like this, 17 times n to the power of 3 plus 3 times n squared minus 2 times n plus 7, so we can write that this function is big O from n to the power of 3, because we can find a constant, for example 20 here, and show that this function from some place will be smaller than 20 times n to the power of 3. For example, c equals to 20, and g equals to n to the power of 3. In fact, we can also write that this is big O from n to the power of 100. This is also true, but big O notation is not the smallest approximation. In fact, such a exact approximation is defined by another notation, which is called theta. Just a second. Maybe some other examples yet. I suppose that you should know this notation because this is frequently used in many situations in computer science, but here on this lecture we denote it more formally to observe some situations. So, for instance, if we write big O from 1, this is a constant limitation in sense that the function is limited by some value. Anyone, because C can be something here. Yes? This is a function. A set of limited functions. For example, such a function f from n equals to 100 or 1000 is big O from 1, because we can find a constant equals to 100 or 101 that this is true. If we take, for example, function -1 to the power of n, so such a function will oscillate -1, 1, -1, 1, and so on. This is also big O from 1, because we can find a constant, for instance, 2, that this is also always smaller for any n. A function 1 by n is big O from 1, because also we can take a constant 1 and from some place this is smaller report. Or logarithm n divided by n, this is also limited. Okay, so this is a set of limited functions. If we take big O from n, this is a set of functions limited by a linear function. Set of functions limited by linear function. So we have, for instance, 10 times n plus 25. This is big O from n. Also, if we take 2n plus 3 logarithm n, this is also big O from n. Logarithm grows smaller than the linear function, and so on. Also, we have a set limited by exponential functions, and so on. However, if we have, for instance, 3 to the power of n, of course, this is not big O from 2 to the power of n. This is a set of functions limited by the exponential function, but the base of this exponential is 2. In fact, n to the power of n and even n factor is not in class of big O from any constant to the power of n. Yes, this is greater. N factor, we can observe in the permutations world, and n factor behaves very strangely. Very strange. This is such a function which behaves as n to the power of n, and it grows extremely fast, and it cannot be bordered, limited by any exponential function with the constant base. Okay, is it clear? I suppose that you know it, but or not. Yes? Okay. So this is big O. A little bit more useful is a function theta, very similar. For example, merge sort is a theta. Theta, this is such a letter, theta, Greek letter. It looks like O with such a line inside. I remember the Greek alphabet, alpha, beta, gamma, delta, epsilon, zeta, theta. Okay. The Greek alphabet is very useful. If you, for example, if you travel to Greek island, if you see like this, what is this? Rhodos. This is a Greek. This is rho, omicron, delta, omicron, sigma. So, if you are in Greek, the understanding of mathematical symbols is very useful. Also, as I remember, I have described telephone. This was written by Greek letters, and if you know alpha, beta, gamma, delta, epsilon, zeta, eta, and so on, so you can read this. Okay. So what about theta? This is similar to big O, theta notation. But the difference is such that you have two functions. So here is the function which we are observing, and we have two constances, and from some place, this is our f from n. Here we have C1 times g of n. This is C2 times g of n, and f is between them in such a tunnel, something. So this is important because notation of big O only assumes that this is smaller than or not greater. So in fact, we can write such a thing that, for instance, n square is 17n square is big O from n to the power of 17. This is true, yes, because this is upper limit. But in notation of theta, 17n squares is not theta n to the power of 17. This is theta of n squared, because you should have upper and lower limit of the same bordering function. So the formal definition of theta notation is like this: that it exists two constances, C1 and C2. Real one, and we have a number, for instance here this will be n0, that for all n greater than n0 or equal, we have that C1 times g from n is smaller or equal to f of n. This is absolute value because of negative values of the function. Usually it doesn't matter. And this is smaller or equal to C2 times Gn. So this is a formal definition, that we have a limit from upper and lower directions. This is quite intuitional, but it seems that if we take the greater growing part of the function, as here, if we have, for instance, 17 to the power of n3 plus n square plus some logarithm or something, we observe the fastest growing part, and this will be this notation in theta. This is very frequently used, but tell us that the class of the function is exactly like this. Not that this is greater, like here, that 17n squares is ocro n to the power of 17. This is not theta, but theta is very useful. A part of theta, we have also small o notation and omega notation, and some others, but these two ones are the most important ones in the describing of the complexity of algorithms, and we will use it to describe algorithm which works on discrete sets and on natural number sets. Okay, have you any questions? I suppose this is the whole material I would like to say today, because the next subject is dividing algorithm and the greatest common divisor. So we need another lecture for this. Let us not start it before. So that's all for today. Have you any remarks, questions? Okay, so question. Thank you very much, and have you a better week than the last one, because as you know we have strange situation of the East. So let us have a nice week and see you next Tuesday. Thank you. Goodbye.
Nice
Thank you
day.
so much.
Thank you so much, everyone.
Thank you.